I'm going to mass out some larger crystals. So these are some crystals, some quartz crystals, and they're relatively higher in purity. And if I put 3 on, we get 44.86 grams. This is sufficient to register really well on my other 2 scales. Here I get 4 digits of precision, or 4 significant digits. Every single digit displaying on the scale is significant. If I move these to the less sophisticated scales, I indeed also see, if I were to go on a close-up look, that this is indeed greater than 44 grams and less than 50 grams.
From these measurements, I would interpret this as being 47 grams after I subtract the mass of the weighing boat. So 47 grams is the measurement this scale produces for the large pieces of quartz crystal. That's 2 significant figures. It is a little different than the digital balance. Nevertheless, it is a measurement. Assuming that this scale is correctly calibrated, this reading would be 47 grams.
I'll try the scale that's in increments of 10. It does move, not by much, but it does move.
Once I put the 3 crystals on the scale that reads every 10 grams, we find that it goes from about 2 grams with the weigh boat to 50 grams. And when I subtract those, I get 48 grams, is the measured mass of the 3 crystals combined. Mass depends on the amount of substance. There is also a way we can measure things based on their type, that is, their density.
Now, if I wanted to investigate, are these large crystals the same material as the small crystals I started out with? Well, density is something that should be about the same. Quartz should have the same density as another piece of quartz, assuming it's pure. Now, some of these do have some impurities. To measure density, I simply need to know the mass and the volume. If I want to measure the volume, there are a few different ways I can do this. Perhaps the easiest way is to use volume displacement. Now, I could use rulers and some fancy math equations, some geometry, and determine what the volume is based on the measurements I make and knowing the shape of these different crystals. But that would be rather challenging. There is a better way. And the better way is volume displacement. To do volume displacement, I simply record the beginning volume. I'm going to use the beaker. I don't happen to have a graduated cylinder that's large enough right now for these large crystals. And so I would record the initial volume, and then I would immerse my quartz crystal. The volume goes up a little bit because the crystal displaces some water. This is water displacement. Volume goes up as I add a crystal. I can add another one. Volume goes up further. And I'm going to add the last one. And the volume goes up even more. I am careful to make note of the volume before I put in the crystals and also the volume afterwards. And I'm careful to make sure the crystals are fully below the surface of the water so I get the full volume. Okay, then I can just simply retrieve my crystals and let them dry off to the side. So I can determine what the average density of these larger crystals are, these well-established, relatively pure quartz crystals. And I can compare that with the smaller quartz crystals. To do that, I will use a graduated cylinder that's more appropriately sized for those. And I fill it up with a small amount of water. I don't want to get it all the way full or not full enough. Here I can make my initial measurement by looking at the lines, and then I can add my first crystal very carefully. The volume goes up ever so slightly, and I can make a reading and determine how much it increased by. Now I'll add my second quartz crystal, and the volume goes up slightly more because the quartz displaced some of the water, and so the water volume goes up, and I can do some subtraction to determine what those volumes are. Now that I know the volumes, I can find the densities.
Larger quartz crystals were more dense than the smaller quartz crystals. There's probably some difference in their purities, whether some impurities are more massive or less massive than others.